50,000 years ago. It's melted northward, and the remnants of that glacier are still up in the Baffin Bay area up around Hudson's Bay. Most of the glaciers that we've seen in the last 2.5 million years have come through this area, one form or another, and we've got about 4 major events that we can follow through this area. So what is a glacier? Well, it's just a big mass of ice. But it's not ice that formed by freezing water. That's the phase change of water, liquid, to solid ice. I'm not doing that. I'm not making glacier ice that way. If I'm doing it that way, I'm not making a glacier. Glacial ice is recrystallized snow. The snow falls in the mountains, it accumulates, just the weight of the snowfall compacts the snow underneath, and as that occurs, metamorphisms occur. Glacial ice is essentially a metamorphic rock. The ice crystals are recrystallizing, they're growing into each other, and when you look at glacial ice, it has this gorgeous dark blue color to it. And that's because of this recrystallization. You don't get that with just doing the phase change of freezing water into ice. Then you got air bubbles and you got all sorts of things going on. Not kind of just clear, maybe milky looking ice. That's different. Another thing that makes a glacier different is that it's on land. It's not out in the ocean. The Ross Ice Shelf is frozen ocean water that went through the phase change, and it's sitting there as this big shelf of ice kind of right along the edge of Antarctica. That is not a glacier. A glacier is up on land. Now, the tongue of the glacier, the end of the glacier, as it's moving and it might go out into the water, it's still a glacier because it's attached to the glacier, but it very quickly starts breaking off and floating away as icebergs. So a lot of icebergs that we see are of glacial origin, but usually when we think in terms of glaciers, we're talking about taking water out of the ocean, putting it up on the land, usually snow, and recrystallizing it into glacial ice. The other thing that it's doing is it's moving. And it's usually moving because of gravity. It's flowing downhill under its own weight. Gravity is just driving it along down the slope. So would I expect to see a glacier that's retreating, be backing up the side of a mountain? How am I going to do that? How am I going to move that mass of ice back up the mountain? Gravity's not going to let me do that, is it? So why is the glacier retreating? Let you think about that for a second. So when we see this recrystallization process going on, it starts out as just a nice old snowflake. We see that the points, the ends of the snowflake starting to kind of disappear. That ion migration we talked about when we talked about metamorphism, it's going on here. The points are going away, the low pressure areas are filling in. It kind of becomes this pebbly looking stuff, and then that firm, that pebbly looking stuff grows together, recrystallizes, and becomes solid glacial ice. So we're looking at metamorphic rocks, essentially. Now, if I've just got this glacial ice sitting there, it's not going anywhere. In that case, we call it an ice cap or an ice sheet. It's not moving. It's not a glacier. And ice caps, like Iceland and the Barnes ice cap, they are less than 50,000 square kilometers. If it's more than 50,000 square kilometers, like Greenland and Antarctica, then we call it an ice sheet instead of an ice cap. Remember the igneous rocks when we talked about stocks and batholiths? how the only, they're the same thing, just different sizes. Yeah, same thing here. Okay, but here's the cutoff is 50,000 square kilometers. So I can look at glaciers. Now let's go back just a second. We can look at glaciers in a couple of different ways. If I look at Antarctica or I look at Greenland, here I've got these glacial ice sheets that cover up entire continents. And I think in terms of these then as continental glaciation. For the most part with Greenland, it's all contained within a ring of mountains that kind of show up right around the edge of the Greenland. So it kind of forms a basin, and that becomes my continental ice sheet. And only at the low passes between the mountains does the ice squirt out as glaciers out to the ocean. So I've got this continental mass now that is just covering everything. It maybe might have a mountain or two poking up through it, but for the most part, it's even covering up the mountains. So it's just kind of sitting there. It's overwhelming the continent. But I've got other ice sheets that aren't that extensive, that aren't that thick. And they're kind of filling in the valleys between the mountains. We call these valley glaciers. And now you can see these things moving, and they're being channeled along the valleys. The topographic low is just like a channel flows with a river. Here, the valley system flows with ice. And a lot of the same principles kind of work. You can see here where a lot of ice is coming down this valley over here, another one over here, and they're all coming together and flowing down this main central valley, just like tributaries in the headwaters of the stream. So, gotta start making this glacial ice, and I'm gonna make it high in the mountains because I can't just have this snowfall that comes every year and then I just melt it every summer. How am I going to accumulate any snow to make glacial ice with that way? I need to be up in the mountains where, yeah, I might have some of the snow melt every summer, but I accumulate more snow than I melt. So over time, it's this continual accumulation of snowpack. So I'm going to have the zone of accumulation high in the mountains. And just under its own weight now, it's going to start moving off the high, down the slope toward the valley. There's my gravity flow for glacial motion. As it starts moving down slope to the valley, it's losing altitude. And it also means it's warming up. It's nice and chilly up there at the top of the mountains. A lot of mountains have a snow cap on them year round. But you come down to the valley, and the valley's nice and warm, and it's comfortable. It's got a great summer. So as that glacier starts moving valley-wise, it starts to warm up. And now I've introduced an issue of melting, but I didn't have that much on the top. For the most part, it was just accumulating. And melting, the fancy word for that is ablation. So somewhere along the journey from the accumulation zone high in the mountains, this ice is moving down into the valleys, and it's going to get to a point where melting or ablation equals the input of new ice from the high accumulation zone. And it's going to look like that's about it, I'm melting it as fast as I'm replacing it. That zone is going to be the equilibrium line. As I continue to put more ice further past that into the ablation zone, I'm going to be melting it faster than I'm replacing it. And it's going to look like actually the ice is stepping backwards. It hasn't reversed. In fact, regardless, it's moving downhill all the time. Gravity's the driver, right? But since I can melt the ice, I can simply melt it faster than I replace it, and it's going to look like it's backing up. remember we said it was a little bit like looking at a river system? Well, I kind of see the same things. If I look at this glacial tongue coming down through this valley here, you put a row of stakes across, and you just kind of watch it for a couple of years, and you'll notice the stakes tend to start to bow across, and the center of the glacier is moving downhill faster than the edges of the glacier. The edges have friction, or they're kind of frozen to the bedrock. They're slow. But the center, just like that main velocity thread in a stream, right there at the top center part of the flow, is the least affected by that bed topography and then those effects of freezing or friction along the bed. So I see again that this top center flow line is the fastest part of the glacier. Same thing if I look at it in cross-section, where the glacier is scraping over the bedrock, there's a lot of friction going on there. Sometimes it's actually frozen right to the rock. And in that case, it's going to go pretty slow. But as I move up into the ice, away from that zone, the ice is going to allow for slippage, it's going to deform plastically, and it's going to allow for faster flow. So if I were to dig a tunnel straight down through the ice to get to the, say, gold that's in the bedrock that the glacier ice is running over, I'd have a problem keeping that tunnel open because the glacier ice would want to keep pushing it downhill, and it would take on this J shape, and I'd always have to be digging my tunnel again. So I've got my zone of accumulation up in the hills. I've got my equilibrium line and the snow line, and that's easy to pick. I can do that just flying over the area because all of this area up here is going to be white because it's getting the new snow. All of this area down here in the zone of ablation is going to be dark because the snow's melting and the dirt that it's carrying is kind of accumulating on the surface. So this snow line or this equilibrium line becomes pretty obvious just from the air. So as long as I'm feeding in more accumulating glacial ice than I can melt, this glacier is going to advance. But if I am feeding in less accumulated glacial ice than the melting, it's still moving downhill. It's still bringing materials along with it. It's still taking up bedrock and bringing it out toward the toe or the end of the glacier. But the glacier looks like it's retreating because the ice is simply melting back, even though in reality it's moving forward. So true or false? Glaciers must change their direction of motion or of movement in order to change from advancing to retreating.
It doesn't move at all.
Just the balance between accumulating snow feeding in versus melting. So you don't have to change direction, you just have to change the balance of input and output. One thing that glacial ice does that makes it kind of a unique material is it will melt under increased pressure. Remember pressure, temperature, they work together. One goes up, the other goes up. Try this someday. It's a kind of fun experiment. You take a block of ice and you put a string over it and you tie a weight on each end of the string. And just throw it in the freezer and let it sit there. Let the weights dangle. And you'll see that little by little, week by week, that all of a sudden the string looks like it's just going right through the block of ice. Somebody snuck in and drilled a hole through the ice, threaded that string through there and retied the weight on the other end. No. What's happened is the string has been pressure melting its way through the ice. Because of the weight pulling that string onto the ice, little by little, that increased pressure under that string has started to melt the ice ion by ion by ion. And each little ion of H2O, a little molecule of H2O makes its way up around the string. And once it's on top of the string, the pressure's decreased, isn't it? It's out from under the string. So it refreezes. And that process continues little by little by little. And given enough time, this string is going to drop out of the bottom of the ice block. Pressure melted. So this is pretty cool in the way glaciers can operate now. So if I look at it, just the weight of the glacial ice at the top of the flow on the glacial ice at the bottom of the flow is going to change the way the ice behaves. At the bottom of the flow, it's going to be under a lot of pressure. That means the temperature is going to rise a little bit, and the ice is going to become more plastic. Kind of like warming up silly putty in your hands. In fact, it can rise to the point that the bottom of the glacier is melted and the whole glacial ice sheet is floating on a bed of water. Whereas at the top, it's going to be colder. There's going to be less pressure because it's at the top. And that means it's going to behave more as a brittle substance, kind of like cold silly putty, where in that case it was pretty easy to just break. So I've got crevasses forming in the top, but at the bottom everything just kind of smushes and flows in a plastic manner. So I see this when I look at the way glaciers move down the valley system. Sometimes I've got these cracks that form on the outer bend of the glacier as it comes around the corner. Why does it do that? Remember in the stream how we had the cut bank on the outside, the point bar on the inside? Because that stream had to speed up on the outside to get around the bigger radius of the bend. And it slowed up on the inside because it was just that little bit right in there around the small part of the bend. Same thing's going on here. So as this ice has to speed up on the outer part of the bend, a lot of tension's put on that, and it starts to break up brittly on the top, and we get these crevasses forming around the bend on the outside. Notice you don't get them on the inside. You only get them on the outside. So if I'm walking along on the top of the glacier and I don't want to fall in a crevasse, where would I walk when I was going around a bend in a glacier? I'd walk on the tight side, on the inside bend, wouldn't I? Same thing happens in a vertical sense. Notice the slope goes over a cliff. The slope increases. And now, instead of being horizontal with the small radius versus big radius, now it's small radius versus big radius on top. And now I get the crevasses forming across the glacier, and whenever I see that, I know there's a change in the bedrock slope going on underneath. And the only place that I would feel comfortable here would be, I would be kind of sticking right to the edge of the glacier, because that's where the ice is kind of frozen to the wall of the valley. And that would be the least likely place that I would see one of these crevasses. So if I were walking down this glacier, I'd just kind of stick to this inside bend and right along the valley wall. Notice that all the other parts of the glacier are deforming nicely. They're behaving as plastic material. Okay, so Greenland, would that be considered an ice sheet?